Okay, hi everyone. Welcome to the course again. This is the part 2 of the transformer model. Okay, in the last class we started discussing different components of the transformer model, and so far we discussed attention, self attention. We noticed that the self attention operation is a linear operation, therefore we had to include some sort of nonlinearity. Then we added feed forward network, right? Feed forward network was a position wise feed forward network, right? So then, in the encoder block we have a in each of the encoder blocks we will have self attention layer and the feed forward layer, right? In the decoder part of it, in every block there is a self attention, masked self attention, right? Because the decoder block should not be aware of what is going to come in the future. In the normal self attention, every attention head has access to all the other positions, right? But in mask self attention, the attention head has access to only the left side of the representations, not the right side. Okay, and we also discussed that in order to basically get an interaction between the encoder and decoder layers, we need a cross attention, right? In which the key will come, the query will come from the decoder part, and key and value will come from the encoder part, right? And then through that, through a normal self attention mechanism, right, we will let the decoder interact with the encoder. Okay, that's what we discussed. And we also mentioned in the last class that transformer model accesses all the tokens in parallel, right? The position information is not properly maintained, right? So in order to let the model understand the position of every token, we need an additional token which is called position embedding, right? The additional token embedding called positional embedding. So we'll discuss positional embedding in today's class. We will first discuss the default positional embedding method proposed by Vaswani et al. In the transformer paper, which is the sinusoidal positional embedding, and then we move to the recent one, which is the rotary positional encoding, rope. Okay, and then we will also talk about some other small components in transformer like add and norm layer, residual connection, and add and norm layer, right? Okay, so this is today's breaking news. So on August 2, Gemini 1.5 Pro, which was released earlier also, it was released I think in February, it was shown to suppress GPT-4o and Claude 3.5. These are significantly larger models on this specific benchmark. This is a chatbot arena benchmark where there are multiple tasks, and most of the tasks are basically ranked, weighted by human annotators, right? You see there are more than 1 million human annotators which are assigned to essentially rank the outputs of all the baseline methods, all the competing methods. And the Gemini 1.5 Pro turned out to be really effective, right? An overall rank of 1 and different task specific ranks, for example math, reasoning, right, coding, and so on and so forth, right? So if you want to know more about this advancement, you can look at the link here. Okay, let's get started. So in the transformer model today, we will focus on positional encoding, add norm layer, and this residual connection. Okay, so let's start with the positional encoding layer. Okay, so this is the survey paper that I would strongly recommend you guys to read. This contains more or less all sorts of positional encoding methods proposed so far. The archive version is more updated. This is published in a journal, but you can look at the survey paper to know more about different types of positional encoding methods. Okay, so in transformer we have already seen that for every token, let's say these are three input words, and these are x1, x2, x3 are the embeddings of the input words. These embeddings can come from a pre-trained model like let's say word to fake or glove kite the models, or it can be a simple one-hot encoding. And what we do next, since these tokens are accessed in parallel, right, just to give more information about the position, what we do, we will add a positional encoding step here, right? Now this is a vector, a positional encoding, a positional embedding is a vector, right, of same size of the input. If the input vector size is 4, this will also be 4, right? So this is the positional embedding for token 1, this is for token 2, for token 3, and so on and so forth. And then what we do, we will basically sum the word embedding, right, the token embedding and the positional encoding, and this will give you the resultant embedding, which is position aware. Okay, now obviously you may ask, why sum, why not concatenation, right? There is no reason behind, concrete reason behind this, but I mean, you can also concatenate the original embedding vector and the positional embedding vector. When we sum them up, the number of parameters that is needed will be decreased, of course, right? Because you are not increasing it to 8 bits. This is still a 4-bit size vector. But there is no concrete reason. You can also concatenate if you want. So this one is these are the position aware embedding, and these embeddings will be moved, will be fed to the first layer of the encoder or the first layer of the decoder, right? Each layer, I mentioned already, each encoder layer consists of unmasked multi-headed self attention, a feed forward network, and there are some components here and there. Each block of a decoder consists of a mask attention, mask self attention, a cross attention, and a feed forward network, right? So the input that is given to the first block, is position aware embedding, right? Now remember, sometimes people think that maybe this position information is added to every input of the layer. It's not like that, right? Say if this is the second layer, it is not the case that I will again add the position information here. The position information will only be added at the beginning, here and here, right? Okay, so what is the simple way of encoding the position information? What do you think? A simple way could be that you can just encode first position by 1, second position by 2, third position by 3, and so on and so forth. Let's say there are 30 tokens. First position will be encoded using this 1, the number 1, the second one is 2, 3, and so on and so forth. This is the simple option. For position 0, the position embedding can be zeros, all zeros, right, in the vector. For position 1, all 1s, for 2, all 2s, and so on and so forth. For 3, all 3, and so on, right? This is not as simple, right? There are many problems. The first problem is that the size of the input, right, varies. The size of a sentence varies. Let's say in one sentence there are 10 tokens, 10 words. In another sentence there are 20 words, right, 20 tokens, and so on. So how do you identify the max number, right? Because remember, the maximum number of tokens should be predefined, right? So how do you identify the max number, because you don't have access to that, and it will also change if we increase the training set. The second problem is the last, let's say there is a sentence where there are only 3 tokens. So the last token embedding is 3333, right, the positional embedding. There is another sequence where the last token is at the 30th position. So the last positional embedding is 30 30 30 30, right? So look at here. So the 3 and this 3 vector and the 30 vectors are different, right? So the model may misinterpret by thinking that this 3 position embedding is same as here, which is also the third position, right? How does the model know that this is the end of the token, end of the sequence? How does the model know this is the end of the sequence? Because here also you have 3 3 3. Okay, so determining the maximum length of a sequence is not possible through this approach, right? So what is the simple remedy to address this problem? The simple remedy is you just normalize it, right? So let's say the max, so in this sequence the maximum number of tokens is, let's say, is 3, right? So you divide everything by 3, isn't it? If you divide it, then the last embedding is going to be 1 1 1 1. Here also 1 1 1 1. You divide everything. So here in this case you divide by 30. So you divide every positional embedding by the max number of tokens present in the sequence, right? Like this. Okay, like this. So now you guarantee that, okay, the last position information will be encoded by all ones, irrespective of the size of the sequence length, right? But there are problems here. What is the problem? The problem here is it depends on the number of tokens in the sequence, right? So when you divide this by 3 and divide this by 30, look at the first position, 0th position, first position. This is the position embedding, 0.33, 0.33 and 0.33, right? And in this case the first position is encoded by 0.2, 0.2, 0.2. Although both of them denote the first position of the sequence, right? But now they are denoted using two different vectors. This is not desirable, right? We always assume that, you know, for every position there should be a unique vector, right? So that the model will also understand that, you know, this is the unique vector. So although this approach addresses the problem of this last token, you know, uniformity, but it doesn't address the problem of two positions should be encoded using same vectors. Okay, what do we do in this case? How do we address this problem? So in a simple way, right? A simple way to address this problem is as follows. Now this is what was proposed in the original transformer paper. Let me first motivate what does it mean. So this is position 0, position 1, position 2, 3, 4, 5, 6 and so on and so forth. Okay, let's assume that every position is encoded by a vector of size 4. Okay, so if I use a binary number concept, right, you can encode this by 0 0 0 0, you can encode 1 by 0 0 0 1, right, 2 by 0 0 1 1 0 and so on and so forth. You basically convert every integer to a binary. So in this way, if you do that, you at least guarantee that all positions will be unique, right? And the model should be able to also differentiate different positions. But of course, adding this kind of binary numbers to a word embedding, which itself is composed of fraction numbers, right? Let's say 0.3, 0.1, and you add a binary vector like 0 0 0 1, 0 0 1 0 to a fractional vector, doesn't make much sense, right? It also suffers from the same problem that we don't know what is the length of the input sequence, right? But we can get motivated by this idea that, you know, if we use this kind of binary encoding techniques, you can differentiate different positions. And how do we encode this kind of thing? How do we encode this kind of representations? Okay, now look at these numbers or look at these vectors very carefully. Let's say this is the least significant bit, LSB, right? Every unique number is altered every second position, right? 0 here, 0 here, 0 0, right, 0. Every number here is altered in 4th position, so here, right, here and so on. Every number here is altered in 8th position, isn't it? So you see some sort of periodicity, right? And we know what's the best way of capturing periodic signal. We use sinusoidal representation. You know, don't get afraid by this formula, I'll explain. Okay. So this is the positional embedding formula that was proposed in the transformer model. If this is the position vector and there are elements in this vector, right? These are different elements, right? First element, second element, and these elements are denoted by I. Okay, so I equals to 0, I equals to 1, I equals to 2, and so on and so forth. Here you see these are elements. Okay, this is a vector and these are different elements. So instead of using 0 1, I will use some trick to essentially determine the value of every element in the vector. Okay, So I denotes the element within the vector, pos is position, right? So position 1, position 2, position 3 and so on, okay, and d model is basically the model size, okay. So in this case the model size is 512, okay. Now the model size is already fixed, it's a constant, right? Position is also fixed, we know the position, and I is also fixed, and we see how we can use this, okay. So let's assume that I would like to encode the position information of the first position. So pos is 0, okay, and the size here is 4, okay. So this I will vary from 0 to 4. Okay, this is I equals to 0, I equals to 1, 2, 3, 4, right? So every element of this position vector will be determined by this formula. So in this case, this is going to be sine, right? Position equals to 0 by 10,000 to the power, let's say you are interested in I equals to 0, right? I equals to 0. I equals to 0. 0 by d is whatever, right? D is a fixed number. So this number is going to be the first element of the position embedding, okay. The second element of the position embedding is going to be, right, sine 0, 10,000, 2 times I, 2 times 1 by d. You may ask why this is the number 10,000 coming here, right? This is just a number that they proposed. And this value determines the frequency of the sine wave, isn't it? Think about it. D is fixed. D is fixed. If I equals to 0 or I equals to 1, I equals to I is a small number, then the frequency will be high, right? If I is a large number, then the frequency will be less. And we know that a high frequency sine curve looks like this, and the low frequency sine curve may look like this, right? So we capture the first or the upper part of the vectors through the high frequency sine wave, and the lower part of the vector by the low frequency. Upper part means I equals to 0, I equals to 1, and so on. So more or less you understood the concept, right? Now let's see. So you may wonder, why do I need this I? Let us forget this I, okay, and let us only embed the positional vector using only the position information, okay. So basically sine position. Now look at this figure here. X-axis indicates the position 0, position 1, 2, 3, 4, and y-axis is a sine value. Look at here. If we do that, the 0th position value and the 6th position value would be the same, isn't it? Similarly, you will see that the first position value and the 7th position value will be the same, right? But all these positions should be unique, right? Therefore, we add the concept of frequency, we add the concept of I index, right? And if we do that, if we add this, then it would look like this. I equals to 0, high frequency, right? You see the high frequent wave, right? I equals to 2, a bit low frequent wave, and I equals to 4, even lower frequent wave, and so on and so forth. So 0, 2, 4, these are different indices in the vector. Now the concept wise, I think this is clear. Now let's look at the beauty of this formula, okay? So let's say there are two consecutive positions, position 1, position 2. X-axis indicates position, okay? Position 0, position 1, position 2, and so on and so forth. And y-axis is the sine value with different eyes. Let's look at two consecutive positions, 0 and 1. Okay, ideally, what do you think? Intuitively, if two words are close by, right, versus if two words are very far, should that information be also captured in the position embedding somewhere else? If you look at this one carefully, 0 and 1, I will call this part of the figure as the low frequent band, and this is the high frequent band. Okay, so two nearby positions 0 and 1, you see that their low frequent sign numbers are quite similar. They will be separated by the high frequent signal. Look at here, right? So they will be separated by the high frequent signals. It means that if you compare two embeddings, right, position 0 embedding and position 1 embedding, right, you will see at the 0th position, 1 positions there are changes, but as we move away, as we move far, I equals to 4, 6, 8, right, 10, 12, 30, 40, you see that numbers are more or less same, right? Agreed? So two nearby positions are mostly separated by high frequent bands, high frequent signals, and high frequent signals are captured by the first few elements of the vector. I equals to 0, I equals to 1, and so on and so forth. Okay. Now as you move on, let's compare the 0th position and let's say 6th position, right? 0th position and the 6th position. You see that the low band, the low signals, low frequent signals, they are itself capable enough to differentiate them. Look at this one. So here you see the difference, mostly the difference here, but here you will see the difference at the low frequent zone. Okay, so when you compare 0th vector, 0th position vector and the 6th position vector, you see that the high frequent regions will of course differentiate them, but the low frequent regions will also differentiate. The best way to visualize this, I have a visualization. This is a visualization. So this is a position embedding of 50 words. Okay, 50 positions. So each row indicates a vector, position vector, right? Each row indicates a position vector. So the first row is the position information of the 0th token, and second one is the first token, and so on and so forth. Each column indicates the elements of the vector I. Look at the first embedding. You see this periodicity here, right? This white block is getting repeated, right? Every single position. If you compare the first two bits here, or first two elements here, you see there's a difference. And these are high frequent regions, isn't it? Because I equals to 0, I equals to 1, and so on and so forth. This is not exactly the sine curve, by the way, because we will discuss it is composed of a mix of sine and cosine. Now let's look at the third important property here. So look at here. There are two positional embeddings for 0th and 6th respectively at I equals to 4, which is the lower frequency range. They are more or less the same, right? As you move on, I equals to 2, you see a difference. Okay, as you move on, as I equals to 0, you further see the difference, right? So at low frequency, the value is exactly the same. This will start to differ significantly as we move to the high frequency zones. Okay, so now the original transformer paper, they used a combination of sine and cosine, right? So this is the formula that they used. Every odd position of the vector, okay, let's say I equals to 1. If I equals to 1, then EI will be 2 and EI plus 1 will be 3, right? So the second element will be driven by sine, and the third element will be determined by cosine. The frequency is the same, this will be determined by sine, and this will be determined by, so this is sine and this is cosine, right? If I goes to 0, then this will be sine, and I equals to 0 means 2i plus 1 will be 1, right? So this will be cosine. So the first element will be determined by sine, the second will be cosine, third by sine, fourth by cosine, and so on and so forth. This is even complicated. So far we have only seen one type of signal, sine. Now here they said let's mix both sine and cosine. Both are periodic and kind of complement. So this will even help differentiate positions further. Let's look at whether this concept is enough to satisfy all the position embedding properties. So it is independent of the length of the sequence, right? It will give same embedding to the same position of in different sequences, right? Okay. Two nearby words will be differentiated by the high frequency region, right? Whereas words which are far will be differentiated by both high frequency and low frequency region, right? So if we take the dot product or some sort of similarity, you will see that the positional similarity between nearby words are quite high, whereas those words which are far, their positional similarity is quite low. Now this is the formula, okay? Let's say the model size is 4, so d mod is 4, and you have sine, cosine, and so on and so forth. So this is the positional embedding, and this will be added to the actual word embedding, okay? And this added vector will be passed to the next layer, the first layer. Is clear? This is just a visualization. You can also just run this and see how it looks like. By the way, so this was proposed in Vaswani's paper, but then later people realized that let's not make it complicated. Let's just consider this position embedding as a trainable parameter. Let's train this positional embeddings, right? So for every position you will have a trainable vector, right, which will be learned, okay? And this position vector will be same across all the sequences that we are going to feed in, right? Let's say you have the first sequence x1, x2, x3, x4, second sequence y1, y2, y3, y4, y5, y6, third sequence z1, z2, z3, okay? The position vector that we will learn would look like this. Let's say p1, p2, p3, p4, right? Plus p1. The same position vector will be learned based on the second sequence, p1, p2, p3, p4, right? And so on and so forth. So you can think of it as a kind of a dictionary where every element of the dictionary indicates the position vector, right? So whenever you feed a sequence, you fetch the corresponding position encodings from the dictionary and you just add them and pass them. And then when you do backpropagation, the position embeddings will also be updated. Okay? So these are the three properties that we generally consider when people think of a new positional embedding techniques, right? The first property is called monotonicity, which says that the proximity of the positional embedding positions decreases when the positions are far apart. I already mentioned, right? Let's say the position x, so this is the vector, right, corresponding to the position, and there is another position x plus m, x plus m, and x plus n. Okay, if m is greater than n, meaning n comes earlier, so x plus n, x plus m, right? So the proximity between this and this should be higher, the difference should be lower, and the proximity should be higher. If two words are close by, right, they are near, their proximity should be higher. Okay, so this proximity will be higher than this one. Proximities can be captured using similarity and any other metric. The second property says it should be translation invariance, meaning the proximity of embedded positions are translation invariant. Now, what does it mean? Let's say x1, x2, x3. Okay, these are three positions, x1, x2, x3, and there's a number m. So x1 plus m, x2 plus m, x3 plus m, right? So you have three pairs now, x1, x1 plus m, x2, x2 plus m, x3, x3 plus m, right? If you measure the proximity, they should be the same. It should not depend on the original position x1, x2, x3. These are basically highlighting the relative positions. Okay, the relative position should be intact. The relative position difference or the proximity between 1 and 3 positions and 4 and 6 positions, right? They should be same. They should be the same. Symmetricity. It is also very obvious, right? The proximity between x and y, two positions, should be same as the proximity between y and x. So if you try to come up with a new positional embedding, these three properties should hold. Okay, so let's move on to the very recent one. In this paper, this is called Rotary Positional Encoding. This was uploaded in 2023, and since then recent methods like PALM, right, GPT, Neo GPT-J, Llama 1, 2, all these models are basically using this positional encoding. Nobody uses the sinusoidal representation. Okay, the idea behind this is a bit complicated, but very different from the sinusoidal approach. Okay, so what is the idea here? By the way, they propose this rope positional embedding, and they just incorporated this rope embedding to transformer, right? And they came up with this model called rowformer. Everything is same except the embedding, and that actually made a lot of difference. I'll tell you. So why position information is so important? When you see the result, you will realize that this is, although it looks like a very simple problem, it's not like that. In fact, if you read the survey paper, you will see so many variants have been proposed so far, with small changes here and there. Okay, so we have seen two kinds of thoughts in designing the positional embedding method, right? One is the absolute positional embedding. In the absolute positional embedding, you are essentially you are only focusing on the absolute positions, right? You are trying to somehow encode those positions, right? So how do we do that? One way is either through learning, right? You basically learn all the positional embeddings, and the other way is the sine cosine based approach that I mentioned earlier. So this is absolute positional encoding. This is just a demonstration of absolute positional encoding that I discussed so far. These notations are important, therefore I am explaining it again. So what is this xi? Xi is the word embedding, okay, input word embedding for the corresponding position I or the word token I, right? So what is fq? Now remember, from every token I generate three vectors: query, key, and value, right? Query will be generated through a function, some function fq, right, which in the normal transformer, this is essentially a linear transformation. You multiply the embedding with a matrix wq, right? We multiply this by wq, and this is by wk, and this is by wv. But let's assume that these are generic functions. Okay, now these are functions of the word embedding and the position m, right? In a normal transformer, what we do, we basically do xm plus pm. Pm is the position information, right? And here xn plus pn, and so on and so forth, right? But again, let's make it generic. Assume that there's a function which is be applied to xm and m, meaning the word embedding and the position, right? Now whether this is an absolute position or the embedding or what, doesn't matter. Then what we do, once we got the query, key, value vectors, we essentially we get the attention score, right? This is essentially query key dot product followed by sigmoid followed by softmax, and softmax will give you a distribution, and then your output is going to be the weighted average of the values, right? The softmax output, right? And this will be multiplied with all v, right? And in the original paper, they suggested this kind of sine cosine based approaches. Okay, so in the relative position, so this is absolute position. Let's look at the relative position encoding. In relative position, the idea is that we don't care about the absolute position. We only look at the relative position between a pair of tokens. So let's say the dog chased the pig. Once upon a time, the pig chased the dog, right? If you look at the relative positions between these two, they are the same, right? Although the two words got swapped, right? And the few tokens, were added at the beginning, but the relative position is the same. The relative position is I mod I minus j or mod m minus n. Okay, so we will basically try to preserve the relative position instead of preserving the absolute position. Let's look at some of the developments, recent developments before rope, right, where people mostly focused on the relative position. Okay, so in this paper, in this specific case, you see here is query key and value vectors are generated, but the query vector has nothing to do with the position. This is just a dot product. This is just a multiplication of the parameter and the word embedding xm. Whereas keys and values, they are in these two cases, they use two positional embeddings. You see the difference between these and the previous one? In the previous one, for all these query key and value cases, you basically add the position and the word embedding. But here, only for the key and value, you add the word embedding and the position embedding. But look at this position embedding very carefully. It is PR, right? Not PMPN. By the way, this the index M indicates the query, and the index n indicates the key and value. Remember, the key and values vectors are generated from the same token, right? So you have a query and keys and values. So this is R. What is this R? The R is essentially the relative distance between M and N. Okay, R is M minus N. Now, if it is arbitrarily large, M minus N, you clip, right? You clip using basically a threshold called R max. If it is very small, again you clip using this threshold R min, right? So the R is essentially a clip, right, of M minus N. If M minus N ranges between R min and R max, then it is okay. If it exceeds R max, you consider R max. If it is below R min, you consider R min. So this is PR. Now, how do we measure this PR? This is trainable. You will learn this PR. This PR is added with the value and key, not with the query. Okay, this is one way of preserving the relative position. The second paper, Transformer Excel, they said that let's look at it in a different way. So ultimately, we will do query key dot product, right? Query QM key KN. Okay, ultimately we'll do dot product, right? And in the original transformer paper, what was QM? QM was WQ XM plus PM, right? What was KN? WK XN plus PN, right? Let us just unfold this. So when we take the dot product of this and this, you are basically multiplying this and this, right? A transpose. This is a transpose because Q transpose K is basically A plus B into C plus D. Okay, and this will result in 4 elements. So these are the 4 elements. Okay, now let's look at each of these elements very carefully. The first element doesn't have any position information. These are just word embeddings of query and key. The second element has a position information of the key. The third element has a position information of the query, and the last element doesn't have any word embedding. These are just two positions. That's all. Okay. So what they suggested is that this n, which is the position of the key or value, right? The position of key and value. Let's replace this by a relative position encoding. So I'm replacing Pn by Pm minus n, and this I will learn. Okay. So whenever you see Pm, it is replaced by Pm minus n. Pn, it is replaced by Pm minus n. Okay. What's the second change? The second change, what they said, is that look at this one, this Pm. What is Pm? Pm is the position of the query, right? They said that we don't care about the position of the query because we have already taken care of the relative position of query and key. Now let's replace this by some sort of bias term or some sort of parameter that we will again learn. Okay. So Pm, you see the Pm is replaced by V. So Pm is replaced by V, but where are this Pm basically appearing? Pm appears here, Pm also appears here, right? So here now these two PMs, when they get multiplied with the remaining part, they'll produce something else, right? So therefore they said, let's not keep the same vector, let's introduce two vectors. So this is V and this is U, because their contexts are different. Okay, so you see V transpose and U transpose here. So what are the changes? Again, the changes are as follows. The position of the key will be replaced by the relative position. The position of the query will be trainable. Okay, there is a transformer Excel paper. Now the T5 paper, this and this I already discussed. The T5 paper, the famous encoder decoder paper that we'll discuss later. In the T5 paper, they said, forget about all the terms. Okay, we'll learn everything. Okay, we'll only keep that term which doesn't have any position, right? And the relative and the other terms, just remove all the terms, all the other terms where the position information is there. We'll learn everything, right? And what they learn something called Bij. What is Bij? Bij looks like this. Looks like very interesting. So so this is B0, right? This is B1. I'll tell you what are they. This is B2. This is B3. This is B0. This is B minus 1. This is B1. This is B2. Right? This is B minus 2. B minus 1, B0, B1, and so on and so forth. What are these numbers? This B0 is the bias or the learnable parameter, which indicates the basically the relative position between a current position with itself, right? 3 with 3, 4 with 4. What is B1? B1 indicates the distance between 3 and 4, or 7 or 8, 1 or 2, right? 2 words, 2 subsequent words. What is B2? 3, 5, right? 11, 13. What is B3? 3 words. What is B minus 1? Okay, 2, 1. Therefore, this is Bij. Okay, and this again, this will be learned, and this will just be added to the query key dot product. Okay, there is another formulation. In this formulation, they said that it's very difficult to learn all these things. Let us keep this term, right? And maybe let us keep let's say this term, and the other terms can be captured using this bias and so on. Okay, so decoder paper, they again modified this one. So this was the original equation. You see, they further modified. They kept some terms, right? These terms, some terms are kept. some terms are removed, some terms are modified, and so on. So these are basically the concept of relative position encoding. Now we will see how these concepts are used to essentially build the rope embedding. Okay, so let's see how we can actually combine the relative position and the absolute position information together. Rope is the first paper which essentially leverages both the absolute position encoding and the relative position encoding together. What is the idea? The idea here is very interesting. The idea here is that the dog chases the pig and the pig chases the dog. The relative positions of dog and pig is the same. And how do we capture this? We capture this using the angle of these two vectors. So dog is an embedding. It is basically a vector. Pig again has an embedding which is a vector. We look at this angle. Okay. If the absolute position of these two vectors will change, keeping the relative position the same, the embedding, these two embeddings will just rotate. Let's say this is the sentence, but the absolute position of pig and dog is different from the previous one, right? But the relative position is still the same. They are separated by two words, right? So we rotate this too, right? This rotation essentially takes care of the change in the absolute position, and the angle takes care of the relative position. Okay, since their relative positions are the same, the angle will not change, but due to the rotation, we'll also capture the absolute position change. Beautiful idea, right? In this paper, they essentially mapped all the embeddings to the complex space. Okay, how many of you remember the complex number? Wonderful. Okay. So please be careful. This is a bit complicated to understand. I will try to. It's a very math heavy paper. I will not go into the very details of the math. I strongly suggest you to read the paper, but I'll try to give you the intuition behind the rope embedding. So rope encodes the absolute position with a rotation matrix. So how do we rotate a vector? We rotate a vector using a rotation matrix. By the way, all of you should know that when we multiply a matrix to with a vector, it is just a linear transformation, right? It's just a transformation. Now, and due to the transformation, it may happen that the magnitude of this vector gets changed, right? But rotation matrix is a special matrix. If we multiply it with a vector, the magnitude will remain the same, but the angle will change. Just to verify, you take this matrix, okay? Cos 90 minus sin 90, sin 90, cos 90, okay? Essentially, this is 0, minus 1, 1, 0, okay? This is the rotation matrix. I claim that this is a rotation matrix. If you multiply this, let's say you apply this rotation matrix to a vector 0, 1. If you multiply, what is going to happen? Minus 1, and 0, right? What is minus 1, 0? Minus 1, x-axis minus 1, and y-axis 0, this one. It basically rotated the vector by 90 degree anti-clockwise. 90 degree, I added 90 degree, it rotated this by 90 degree. Okay, so we use the concept of rotation matrix. Rotation matrix is always orthogonal and so on and so on. There are many interesting properties. Okay, so we will incorporate the absolute, we'll encode the absolute position using a rotation matrix, and this is important. We will incorporate explicit relative position dependency in self-attention formulation. We will see later when we calculate the self-attention formulation, the dot product between query key, right? We will see that there the relative position between M and N will be preserved. You don't need to do it explicitly. Okay, if it is not clear, it will be clear very soon. Okay, now let's look at the requirement that they basically considered. So what is this XM? What is XM? XM is the xm is the query embedding, right? xn is the key embedding, right? m is the query position, n is the query key position, right? So they said that I will try to come up with such a formula or such a function fq, fk and g which will basically follow this property. What does it mean? So the function here which is applied to the query and the function here which is applied to the key, these are dependent on the position information, the absolute position information, m and n. But this dot product of these two functions, right, should be same as a g, another function which will be a function of the relative distance of the two positions. I will try to come up with such an f, q, fk and g where fq and fk are dependent on the absolute position, but g will be dependent on the relative position. And when I do the dot product between fq and fk, right, the resultant value would basically be the same value which will produce with using g. Okay, and one of the options of which basically satisfies this is as follows. So fq, they said that fq can be written in this way. Remember what is fq? Fq is the transformation of your query embeddings and the positions, right? So they said that we already know this one, xm and wq. xm is the word embedding and wq is the query matrix that we learned. We will introduce this factor, which is this is e to the power I mq, the imaginary part of the part of the vector. E to the power I is this imaginary part. What is m? M is the position of the query. What is theta? Theta is the rotation value. So I will capture the position information using this imaginary component. Okay. So why this is a natural choice? I'll tell you why this is a natural choice. Similarly, for the key, I have wk and xn, right, and e to the power I n theta, m theta and n theta, the same rotation value theta. Okay. Now if you take the dot product, when we take the dot product between the two complex numbers in a polar coordinate, right, what will happen? Right, x, let's say xi, xj, you take the dot product, right, this will be xi, let's say xi is, how do you represent this in a polar coordinate? R theta, right? So ri, let's say this is ri e to the power theta I, and this is rj e to the power theta j. Okay, when you take the dot product between ei, ej, zi, zj, this is going to be dot product zi, zj complex conjugate. How many of you remember complex conjugate? Right, go back and check what is complex conjugate. Okay, when you do the complex conjugate, it is essentially saying that ri, rj e to the power theta I minus theta j. Okay, so if you do the dot product between these two, this will result in this one, wqxn, wkxn, right? This wkxn star, what is this? This is the complex conjugate of this one. This is z1, this is z2. I'll have to take the complex conjugate of z2. So this is complex conjugate, and e to the power I m theta and e to the power I m theta. So e to the power I m minus n theta. Okay. Now the interesting part is, look at this m minus n. So now this is my g, and what they said is that when we expand this, right, cos theta plus I sin theta, right, I will only take the real part of it, not the imaginary part of it. So the real part is going to be the output of g. So g would look like this. Now let's see whether these three things satisfy the property that I was mentioning earlier. fq is a function of m and xm, fk is a function of n and xn and n, where g is a function of xm, xn and m minus n. Okay, all right, few more maths. So this e m theta, right, again if you remember the complex number, right, e m theta can be represented using Euler's formula, right, which basically says that e m theta is nothing but a matrix like this. Again, if you are not convinced, go back and check. Okay, so this is e m theta is nothing but a matrix like this, which is a rotation matrix. So you are applying a rotation matrix with this transformation, right? You are applying this rotation matrix with this transformation. So this is the rotation matrix, this is W matrix, and this is the embedding. So when you multiply this with the linear with this weight, it will produce a vector. This vector will be multiplied with the rotation matrix, right, and that will essentially rotate. Okay. Now, whatever I mentioned so far is for the two-dimensional case, when the size of the vector is 2. Now, what happens if the vector is of n dimension, right? If the vector is of n dimension, then this rotation matrix would look like this. What is this? Let's say the d dimension, right? You have d by 2 number of small blocks, diagonal wise, right? This is the first block. Okay, this is the second block, this is the third block, and so on, d by 2 number of blocks. What does it mean? Can somebody tell me what is happening here? If, think about it, if there's a vector of size d, right, you are taking every 2 elements of the vector and you are rotating. You are taking every 2 elements of the vector and you are rotating. Okay, remember we also need to preserve the all these properties, right? I mean the unique positional embeddings, the relative positions, and so on and so forth. And how do you determine this theta? Theta is essentially same as this Vaswani's paper, right? 10,000 to the power minus 2 times I by t. Okay, are we learning something here? In this case, look at this, the numbers, all this formula carefully. Are we learning something here? Are we learning something? We are not. W's are trainable parameters, is already there, right? We are not learning the position information at all because theta is already given. Theta depends on I. Okay, now when we take the dot product qm transpose kn, right, what is qm? Qm is this rotation matrix times wq times xm, right? What is kn? Kn is another rotation matrix, right? Wk xn. If you multiply, if you do some arrangement here and there, you will see that you will get a matrix which looks like this, rotation matrix which looks like this, right, which we call R, right? R is basically a function of m minus n. Okay, so when we do attention, self attention, you basically preserve the relative information. Okay, so the statement that I mentioned earlier incorporates explicit relative position dependency in the self attention formula is there, encodes absolute position with the rotation matrix is there. So rotation matrix takes care of this m and n, right, m and n. When you do self attention, you see the relative position is preserved. Okay, this is a great paper, I would say. If you read the math, you'll be basically amazed. Okay, so these are some of the properties. In contrast to the earlier position embedding method, rope is multiplicative. Remember this, that I forgot to mention. The position information is not additive here; it is multiplicative, right? This is multiplicative, isn't it? Multiplicative. Rope naturally incorporates relative position information through rotation matrix, right? instead of altering terms that I mentioned earlier, and the rest of the things I already mentioned. You can, if you go through the slides, you will realize. Okay, let's look at some of the again just two properties. We are almost there. If I plot the relative distance between tokens 2, 3, 4, 5, 6 and the relative value of the position encoding, you see that with the increase of the relative position, the proximity value of a pair of positions, right, pair of position embeddings will decrease, which was one of the properties, right, that with the increase of this it should decrease, right, x plus m and x plus n, remember. The second good thing is that although this matrix looks like a very gigantic matrix, right, but most of the entries in this matrix are zero, right. So if you do some small math here and there, if you see that this can be realized by this, okay, where you look at the cos part, you segregate the cos and sine part, right, and you multiply one part of the embedding with cos, another part of the embedding with sine. So this is also computationally very efficient. Let's look at the result. Okay, so this row former was tested with the original transformer paper on the machine translation task, German to English to German, and there is a small blue score improvement, right. Row former was also tested with the BERT model. Okay, it showed significant improvement. Remember, we just added the positional information, just change the positional information, remaining part is the same, right. With such change, there's a gain from 71 to 86, 85 to 87. Not only that, but also in the training time. So this is the x-axis indicates that the training time step, right, and y-axis indicates the loss. You see, so this orange line is the BERT and the original BERT without rope, right, and this blue line is the row former. You see that the model also converges faster than BERT. Okay, now if you see the there is another model called performer. There are different transformer versions, long former, performer, and so on. So in the performer model, if we use rope and if you do not use rope, so performer with rope, performer without rope, you see again the loss decreases quickly compared to the case where there is the the normal positional embedding. Okay, so this is all about the rotary positional encoding part. So we have discussed what? We have discussed positional encoding, right? Positional encoding, and the other modules are also discussed. What are remaining? One part which is remaining is a residual connection. We all know what is a residual connection. So let's say this is a layer, right? This is x, okay, and this is basically a function f(x). It will produce f(x), right? So I will basically have a shortcut from input to output, which will basically add the output with the input. Okay, now this will be fed to the next layer. Instead of feeding f(x), I will feed fx plus x, right? Now why this is important? This residual connection is important because it helps you address the vanishing gradient problem, because now you have a direct connection, right? You are not letting the gradient flow through the complicated portions of this f block, right? It can flow through this directly. This will help in convergence, and there are many important properties. So what we do, we add a residual connection here across self attention. You will add another residual connection here across this feed forward network. Okay, the last part is this add norm. Add means the residual connection add, and what is norm? Norm is layer normalization. What is a layer normalization? So let's say when you do some complicated stuff within a layer, within a specific layer, let's say the layer is the self attention layer, right? You basically result in a vector, right? Now this vector, sometimes due to these operations, some of the properties of these vectors get changed. Now what are these properties? When you try to make the model fast, fast in terms of convergence, etc., we always make this vector as smooth as possible. Now what do you mean by smoothing? Basically, a smoothing means that I want the elements of the vector to basically follow certain distribution, right? Let's say you follow a distribution where you have 0 mean and units standard deviation. In that case, what we do, whenever you obtain a vector, I basically apply another formula, right, where I make sure that all these elements basically ranges between 0 and 1, right, and it also follows certain properties and so on and so forth. Okay, let's now look at the batch and layer normalization, which is essentially one of the components of the transformer model. If you remember the architecture once again, right, we had input, positional encoding, right, multi-headed self-attention, feed-forward network, right, and residual connection, and then we have this add norm layer, after every subcomponent of a layer, right? After every attention layer, we have this add norm. After every feed-forward layer, we have an add norm, and so on. Similarly, in the decoder, you have add norm here, add norm here. Look at here. After mask attention, you have add norm. After cross attention, you have add norm. After feed forward also you have an add norm layer, right? So let's look at what this what is the function of this add norm layer. So add corresponds to this residual connection. You are basically adding the input to the output of the layer. Okay. Let's look at the normalization part of it. Now, the normalization of a vector or of an output, right? It is not restricted to transformer model. It is used, all over the neural networks. Any deep learning model, when you design, we always try to add this normalization layer after every block, okay, after every layer. There are multiple reasons behind this, and what is this normalization? It essentially, this function, this is operated on a specific vector, okay. Now this vector is, the vector can be a single vector like an output vector. In this case, let's say a vector can correspond to a token, right, or a vector can be a concatenation of multiple vectors and so on, okay. So what is the purpose of this normalization layer? The purpose is that I will try to essentially, after every layer, since there are so many operations within the layer, it may happen that the entries within a single vector get deviated, right, and it may not start following a certain pattern, right. What do you mean by a pattern? A pattern can be, let's say, you want to make sure that the entry, all the entries in a specific vector ranges between 0 to 1, for example. Or let's say you want to make sure that the entries actually follow a certain distribution, okay. Now this pattern actually gets changed when you move from one layer to another layer due to these complicated operations within a layer, okay. So therefore we do this normalization. Normalization has a series of benefits. The first benefit is that if we do normalization, it will help you stabilize, it will help you speed up the training process, right, by keeping the inputs to each layer within a similar range or within a similar distribution. It ensures that the gradients don't explode or the gradient don't vanish during backpropagation, right. It also is very effective in accelerate the convergence, right. There are empirical studies which showed that if you use normalization versus if you do not use normalization, right, in the former case the model converges faster than the later case. The third advantage is preventing overfitting, right. There are methods like dropout, some of you know in the deep learning, right. In deep learning we use these dropout techniques where we essentially freeze some of the weights, and along with dropout and normalization, it also helps address the overfitting problem empirically. And essentially, if you think of all these 3 points together, it essentially improves the gradient flow, right, across the layers. So normalizations can be of different types: batch normalization, layer normalization, instance normalization, weight normalization, group normalization, and so on and so forth. But in this specific part of the lecture, we'll focus on batch and layer normalizations. So in transformer, we generally use layer normalization, but batch layer normalization can also be used. We'll look at the pros and cons of batch and layer normalizations, okay. let's take an example to illustrate the idea of normalization. Let's say you are given a instance where there are two features. One feature is the age of a student, and the other feature is the tuition fees, right, in an academic year. So based on the age of a student and the tuition fees, you want to determine whether the student is eligible for taking a loan or not, right? So here the age ranges between 18 to 25. Let's say you have a feature which ranges between 18 to 25, whereas the tuition fees in an academic year ranges between 20K to $50K. Okay. Now you see, if you look at these two features, now these two features essentially correspond to two entries in the vector, right? And the ranges are very different. So one way to do this normalization is that you make sure that all these entries range between 0 to 1. How do you do that? One way of doing this thing using, right, you can use this kind of min-max normalization. You subtract every entry by the mean entry of the feature, right? Like let's say the feature is age, right? You look at the minimum age present in the training set and you subtract that minimum value of that feature from the element, from the entry, and the denominator is the max minus mean, max value minus mean value. So let's say the max value is 25, mean value is 18, so it is essentially 25 minus 18, and it makes sure that this will always be between 0 to 1. Okay. Of course, there are other ways also to make sure that the range is between 0 to 1. Now this is called normalization. There is another term called standardization. In a standardization, what we do, again given the two features, age and tuition fees, right? What we do, we will make sure that these two features follow a certain distribution. Okay. Let's say we make sure that the distribution, in this distribution the mean is 0 and the variance is 1, right? How do we do this? For every feature we calculate the mean, right, and the standard deviation, and we subtract the mean from the element, from the value, and we divide it by the standard deviation. If you do that, it doesn't guarantee that it ranges between 0 to 1. It will not be 0 to 1 at all, right? But it will follow a certain distribution where we see that the mean is going to be 0 and the standard deviation is unit. Okay. Now this is called standardization, but oftentimes we will essentially use standardization and normalization interchangeably. Okay. Now let's focus on batch normalization. In batch normalization, what we do, we'll perform the normalization operation after every batch. So we'll send a batch, right? We will stack all the outputs of the batch and then we will do the normalization, right? Let's first look at the batch normalization properly. Okay. Let's assume that in a batch, now batch is what? Batch is a collection of training instances, right? So let us assume that in your batch there are 3 instances. This is the first training instance, second training instance, and third training instance. So the column corresponds to the column indicates a feature vector, right, or a vector. In batch normalization, what we do, you take every element of the vector. Let's say you focus on the first element, okay, first element of the first vector, the first element of the second vector, and the first element of the third vector. You look at the first element of every vector, and then you do the standardization, meaning you calculate the mean and standard deviation, right? Let's say the mean is 4 and the standard deviation is this one. Okay, then you essentially subtract the mean from each of these elements, right, and divide this by the standard deviation. Now this is batch normalization, where we are looking at the batch, all these instances of the batch, and first element of that instance in the first element of every vector, right, and you are essentially calculating the mean and standard deviation, right? Now this is happening for instance for entry 1, for entry 2, for entry 3, entry 4, and so on and so forth. So you are looking at all the instances within the batch, and then you are doing this operation. This is batch normalization. What is the problem here? The problem here is that your batch should be representative enough. The batch should be representative enough of your entire population, of your entire training set, right? If your batch size is very small, this mean and standard deviation, remember the mean and standard deviation will vary when we basically feed another batch, right? So for a particular batch, you have a certain mean and standard deviation. When you feed another batch, the mean and standard deviation will change. Okay, so if the batch size is not large enough, right, you may not be able to basically get the correct distribution of the population. Okay, mathematically, how do we formulate it? Look at here. There are b number of instances in the batch. Okay, and across the batch, you are taking the mean and standard deviation, right, for a particular element, right, and you subtract the mean from the element and then you divide it by the standard deviation, right, and this is happening for a specific element I, right. So I is the index ranging from 0 to d is the vector size. Oftentimes what we do, along with this batch normalization, we also add some trainable parameters. So let's say this is the updated value of the element. Along with the updated value, we add some sort of gamma and beta, right? And these gamma and beta are basically learned during the backpropagation time. Okay. So the first limitation, as I mentioned, if the batch size is small, the sample mean and standard deviation are not representative enough of the actual distribution, right? And the network may not be able to learn the actual meaning. Okay. This is not very suitable for a transformer kind of model. Why? Because in a transformer kind of model, which is a sequence model, the sequence length actually varies, right? Let's say you have a batch where there are sequences of length 4, there are batches where sequences are of length 8 and so on and so forth. So this may not be a suitable option for that kind of cases, right? And you easily understand why. Let's say there's a batch where there is one sequence of size 4, another sequence of size 8, another sequence of size 16, right? How do we do this mean, right? Because right, in the second instance you have this fifth element which is not present in the first instance. So when this varies, this may not be a right approach. Okay. Okay. So in layer normalization, what we do, we will not look at all the instances of a batch. There is no concept of batch here at all, right? We look at every vector and all the elements of this vector will be used to calculate the mean and standard deviation. Okay. Here again, every column indicates an instance, right? I will look at column wise entries and then I will basically measure the mean and standard deviation. So 1, 3, 5, 7, mean is 4, standard deviation is 2.23, then I subtract this 4, right, and so on and so forth. So this will make sure that each vector follows a distribution, right? The distribution may vary across vectors, but every vector follows a distribution. Okay, look at here, there are d dimensions. For every dimension we basically, there are d dimensions, and then for every element, for every instance, I measure the mean and standard deviation, then I subtract the mean from the standard deviation and the mean from the element, and this is the standard deviation. Here also I will use two learnable parameters if needed. Okay, let's look at the difference between batch and layer normalization. What do you think? Batch I already mentioned that so in batch normalization, each feature, right, it normalizes each feature or each element, each entry in the vector independently across the mini batch, right? And in layer normalization we look at one input and then we look at all the elements of that input and we do layer normalization. So batch normalization is dependent on the batch size, right? Layer normalization is independent, right? But if the batch size is small, it will affect batch normalization, but layer normalization is independent of the size of the batch, right? Doesn't matter. Batch normalization requires different processing at the training and inference time. Now look at this one, right? What does it mean? It requires different processing at training and inference time, as in layer normalization is done along the length of the input to a specific layer. The same set of operations can be used as both training and inference times. Okay, so we have actually described all the components of transformer, right? We have described positional embedding. We have described two ways to do positional encoding, right? The sinusoidal operation and rope, right? We described residual connection. We described feed-forward network, right, which is responsible for doing nonlinearity. Every encoder block consists of mask, self-attention, and feed-forward, and two add norm layer and two residual connections, right? And you repeat this n blocks, this block n times, right? In the decoder part, since this is a decoder block, you do mask attention, and then this cross attention. In the cross attention part here, the query comes from decoder, keys and values will come from the encoder. One point to remember is that it is not the case that the first layer of the decoder will basically attend to the first layer of the encoder in the cross attention formulation. It will not be like that. Okay, every layer of every decoder layer will attend to the last layer of the encoder block. Okay, so you have n blocks stacked, and the last layer of the encoder block will produce your keys and values. Now every layer of the decoder will attend to those keys and values. Okay, so this diagram may be a bit wrongly represented, but I hope you understood. Then feed forward network, right? So now I have never mentioned how this model is trained, right? There are so many parameters. How does this model will be trained? Now, when these decoder blocks are stacked, right? After the decoder block, let's say you want to perform some task, and in transformer the paper, the task was machine translation, right? So next word prediction, given a source sentence, you basically predict the target sentence. You generate the target sentence, right? So what you do, so you have this decoder block, right? Every token you need to predict, right? So you feed start token, it will generate something that will come during the inference time, that will come to the next place, it will generate something, and so on and so forth. Now during the training time, what is going to happen? During the training time, remember, transformer will perform all these sequences in parallel, process all these sequences in parallel, right? So during the training time, you already know the translated version of the input, right? So all this, so let's say this is the last block, okay? This is the last block of the decoder, right? Now each of these blocks, each of these heads, each of these tokens will be fed through a linear layer, right? Followed by nonlinearity, softmax. Linear layer followed by nonlinearity. It will essentially produce a distribution, and from that distribution you pick the you sample a specific token, right? If it is deterministic, you take a greedy you use a greedy approach. You take the token which has maximum probability, right? You also know what is the ground truth token at that position, because in the training set you already have the translated version, right? So you can basically compute the error, right? Some sort of cross entropy error, right? And that gets back propagated. So all this at every position of the decoder block, you compute the error in parallel. Unlike RNN, where you need to do this sequence, here you are doing in parallel, right? So either you can sum them up and then take the total error and then you backprop. I think or let's say you take each of these errors in isolation and then you backpropagate. So better way is you just sum them up and then do the backpropagation. This backpropagation essentially happens in end-to-end fashion, meaning it will basically come, the gradient will flow from here to here, gradient will also flow from here to here, right? So all the weights of the layers, weights corresponding to the add norm layer, weights corresponding to the feed forward mask attention, self attention, and also weights corresponding to the input embeddings. If you feel that during the you need some trainable parameters in the input or in the position embedding, for example, right? I mentioned in the previous part, there are certain cases where we use trainable parameters in the positional embedding, right? So those parameters will also be updated, right? Now think how the volume of data sets that are needed to essentially train the entire network. Okay, we'll talk about training later. Now this feed forward network will act as a nonlinear module. This will essentially, this self attention will help you pass messages from one head to another head, right? One position to another position. I mentioned earlier that the self attention is nothing but memory fetching operation, and this add norm layer will also help you reduce the covariance shift. What is this covariance shift? This is another important part of the normalization layer. What is covariance shift? When you move from one layer to another layer, it may happen that the entire covariance of the population gets changed because of this operation, right? So if you do normalization again and again, it will essentially reduce the covariance shift across different layers. Okay, and then you have this mask attention, which will help you prevent the attention looking up into the future decoding states. This is all about transformer. Okay, so in the next lecture we will talk about pre-training. Okay, we'll discuss different types of pre-training techniques, Elmo board, right? And then in the subsequent lectures we'll also talk about GPD and T5 models, encoder only, encoder decoder only models. Okay, thank you.